Good morning, everyone. This is Dr. Neetu Talreja. My today's topic is photocatalysis for degradation of antibiotic and bacteria using metal-doped bismuth oxyiodide. So first, I would like to introduce what is antibiotic, especially tetracycline. So here I have taken tetracycline. Tetracycline is a broad-spectrum antibiotic and one of the most commonly used drug for prevention and treatment of human and animal bacterial infection. TC antibiotic are one of the third most consuming and produced antibiotic due to their broad spectrum advantage. TC antibiotic easily enter into the ecosystem and environment due to their partial metabolization within the human and animal bodies that leads to environmental toxicity, thereby affect aquatic and terrestrial animal. Therefore, there is a need to remove TC antibiotic molecule from environment to protect environment as well as human health. So why photocatalyst material? Numerous processes such as adsorption, ion exchange, reverse osmosis, ultrafiltration, ozonation, electrochemical oxidation, nanofiltration, biological treatment, and photocatalysis have been used to remove the TC antibiotic from the environment. Among them, photocatalysis or advanced oxidation process based on semiconductor material increase attention due to its potential applicability in various end applications such as solar fuel production, CO2 capture, water pollutant degradation, and biological degradation. So why bismuth-based photocatalyst material are required? So semiconductor bismuth oxide-based photocatalyst material continuously gaining attention due to its excellent visible region adsorption, low band gap value, as well as it utilizes bismuth 6s and oxygen 2p orbital in valence and conduction band. Therefore, band gap and band gap edges can be easily tuned by simple modification within the bismuth oxyiodide based photocatalyst material. However, less photodegradation ability still needs the modification in their electronic structure. In this context, the researcher focused on the development of newer bismuth oxyhalide-based photocatalyst material by incorporating metal and non-metal within the bismuth oxyiodide structure. So, how we synthesize bismuth oxyiodide is photocatalyst material. So, synthesis involves uh, the mixing of bismuth nitrate and Ki salt in ethylene glycol, then kept under solvothermal reaction for 24 hours at 120 degrees centigrade. After that, we get the sphere of bismuth oxyiodide, which are very porous. After this process, we start second process in which we use different metal like iron chloride and zinc chloride for the doping. So here we perform XC2 doping. In this, we just kept the salt with the bismuth oxyiodide sphere for 24 hours. After that, vacuum drying, then we get the metal salt over the surface of bismuth oxyiodide microsphere. Here you can see the same images of bismuth oxyiodide based microsphere doped with bimetal, iron and zinc. So magnified images shows the porosity, large porosity and large pore volume of the over the material uh, by assembling the nanosheet together. EDX images shows that both metal are equally distributed over the surface of bismuth oxyiodide sphere. We perform different kind of experiment using tetracycline. So here we have taken the concentration of 1 to 10 ppm of tetracycline, and we use different kind of semiconductor material, metal doped and without metal doped, to check the degradation of tetracycline in water solution. So here we have used bismuth oxyiodide, iron based bismuth oxyiodide, zinc based bismuth oxyiodide, and iron and zinc bimetallic bismuth oxyiodide. And you can see here the maximum degradation was observed using iron and zinc based bismuth oxyiodide microsphere, which is around 86% at 10 ppm of concentration. Band gap value shows that shows this diagram shows that the least band gap was found using bismuth oxyiodide, which is equal to 2.1 electron volt. This is very low for the electron to move from valence to conduction band. Then we check the photocatalytic degradation at different concentration from 1 to 10 ppm, and we found that on increasing the concentration, degradation decreases. So the best concentration was 1 ppm, where the maximum removal was 96%. Here you can see the UV visible spectra from where the percentage degradation, from where the peak is decreases with time. We also check the pH and recyclability of the material. So basic condition are the best condition for the degradation of tetracycline, and almost 96% degradation was found at 10 ppm of concentration. While using acidic concentration, the degradation was decreases and reaches up to 60%. So for a best photocatalyst material, the stability point of view is very important. So here we check the number of cycle and up to and how long photocatalyst can be work. So here we check up to 5 cycle and we found that the percentage degradation insignificantly dropped up to 5 consecutive cycle, and it is almost equal. So there is no significant changes was found in the degradation of tetracycline. We also check the TOC, and up to 60 minutes, we found the 100% TOC value. Then we use different kind of semiconductor material for biological degradation using solar radiation. So antibacterial test assay, here is the result of antibacterial test assay, and we can see that number of colonies decreases using bimetallic doped bismuth oxyiodide based photocatalyst. So here we use two different kind of bacteria, E. coli and S. aureus, and we found that on increasing the concentration, uh, and mm, and here we found that using 1:1 FEZ and BIOI based photocatalyst, number of colonies reaches up to zero value within 24 hours. In case of E. coli and S. aureus, we also check the effect of light and dark, and we found that uh, on passing the light, the number of colonies decreases. Here you can see the same images of E. coli before and after exposure. So after exposure, the cell is almost degraded. In conclusion, we can say that FeZN based BIOI based photocatalyst material have been successfully synthesized using a solvothermal process followed by ex situ metal doping for the photodegradation of TC antibiotic and bacteria. The highest efficiency of TC degradation was achieved using FeZ and BIOI 1:1 based photocatalyst material. The maximum degradation of 96% was achieved using FeZ and BIOI at 1 milligram of TC antibiotic concentration. The high degradation efficiency in the FeZ and BIOI based photocatalyst material was observed due to the large surface area and large pore volume. Therefore, the synthesized FeZ and bismuth oxyiodide based spongy microsphere could be a promising photocatalyst material for environmental pollutant degradation. So, the author acknowledged the financial support from the government of Chile through fungicide project number 3190515 and 3190581. Thank you everyone for listening the presentation.